Morning, guys. So yesterday we had a look at our first projectile motion setup. Basically, projectile motion will be a two-dimensional kinematic problem. We found that because the horizontal and the vertical are completely independent of each other, we actually could set up two columns. Here's what I know about x, here's what I know about y. We can do those kinematic equations again, all the ones on your formula sheet here. For those equations, you can only do it just with x values or just with y values. Don't accidentally use some x values and some y values in the same equation. The only variable that we saw that can jump between the columns is actually time, because time is actually a scalar. So let me just start off with a quick example of this one here. Again, I'm just going to play around with what's the unknown in this problem, but so far it's just been a meatball style question. So we're going to have here, I have my cliff again. This time I'm going to give you the height of the cliff is 50 meters. I'm going to give you the range. Remember, the range was a term we said from yesterday. Range is the distance from the distance from the base of the cliff. It's how far away do I land. Let's say it's 75 meters. So this time here, this car here is zipping away. It's going to travel through this parabolic motion and ends up hitting a target some 75 meters away. This time, my initial question is going to be, well, what's my initial speed? How fast would I have to be zooming so that if it only fell through 50 meters worth of distance, it's able to hit 75 meters? If I have a speed that's too fast, I'm going to end up past 75. If it's not fast enough here, I'm going to end up before 75. What's the perfect speed that I need to have so that it actually ends up exactly at 75 there? So I'm going to give you part A, B, C. Again, don't get scared away when they give you these little part motions here. Actually use them as hints and say, oh, they want you to find A first, then do B, then do C. So first part, I want you to calculate the time to reach the bottom, right? The total flight time, the total time I'm in the air for. B, I want you to find the initial horizontal velocity. So it's the x velocity at the beginning. The x velocity actually doesn't change because there's no horizontal acceleration. And then C, I want you to determine, just like you practiced at the end of yesterday's class here, determine the final velocity right before hitting. We're going to come back in a later unit called momentum. We're going to deal with collisions, how momentum is conserved. We can deal with the aftermath after it collides later on. In this case here, we're interested in the speed. No matter how vertical looks here, calculating that diagonal, calculating what that VF is, we'll need to do a little bit of triangle work. I'd encourage you to pause the video and just try it out for yourself. And then when you unpause, you can have a look at what we have. In starting off, I see that this projectile motion here is a two-dimensional problem. So let's just set up our two sides here. I have what I know about x, what I know about y. In terms of the x, I don't know the initial velocity, right? That's one of the things I'm calculating in B here. What's the initial velocity in the y direction? Well, for the vertical, this one here, the second that it leaves a cliff, the second when I start my clock, gravity hasn't had time to actually speed you up yet. Initially, it's not going up or down, so vertical in the y direction is actually 0. For the 50 meters, I know this car here is going to eventually drop through this distance of 50. So the displacement in the vertical, I want to say 50, but again, because I'm starting out high and I'm ending up lower than my horizontal, I want to actually put in a negative because that means below. I'm just adding positive and negatives just to indicate direction for me. The distance in the x we actually know as well. So sometimes they just call it x. I'm just going to call it d for now. The distance is 75. That's a positive number. So I end up 75 meters to the right of my picture here. In terms of the accelerations, remember we said no x acceleration. So this one here assumes that there's no air resistance. I'm going to pull up a quick simulation later on just to show you in case there is air resistance, how it might change things. But acceleration for all our questions pretty much are going to be 0 for the x. In the y, we have gravity. Gravity is going to be 9.8. So by separating the two columns here, it sort of guarantees you don't accidentally try to use a formula with some x numbers and some y numbers. Start off with the side that you happen to know more. Usually I find I do happen to know more on the y side, and even more of a hint here, usually when you do the y side, you actually use our equation d is equal to v naught t plus 1/2 at squared. Again, the reason why we tend towards this formula here is because this one here doesn't rely on v final at all. In fact, we're going to use those other two formulas to calculate v final afterwards and then do Pythagoras for part C. So if I don't really care about v final, let me just punch in my values. I need to fall a distance of 50, so negative 50. My initial velocity is 0. That's really nice for a meatball style question. The 0 times t kills off that the t term. we're going to see in our football style question a slightly different math because that term isn't killed off. Acceleration is negative 9.8, and then we have our t squared again. Great, one equation with one unknown, so we can solve it. So negative 50 is equal to negative 4.9 t squared. T squared is equal to 50 divided by 4.9. This gives me here, give or take 10.2 or so. I'm going to take the positive root out of this here. Root of 10.2 gives me about 3.2 seconds. So if you just sort of look at the math there, because I know the height of the cliff is 50, gravity needs to drop you 50 meters. Because gravity pulls you downwards at a rate of 9.8, and we actually know it's going to take gravity 3.2 seconds to actually drop you to the ground. Those 3.2 seconds are exactly the same 3.2 that this car here can actually go forwards. The instant that this car here leaves the cliff, right, it was going at some initial velocity. A little bit later, even though it actually falls down this parabola, the x velocity is the same. The x velocity is the same. This x velocity here has 3.2 seconds, and we know it actually covers a distance worth of 75 meters. So we just have our basic motion equation here, d is equal to vt. Because there is no x acceleration, that half at squared term drops out. If I intend to travel 75 meters, I don't know my initial speed, but I have 3.5 seconds before I hit the ground, before I say stop. So that velocity in the x direction here, notice it's not initial or final because the speed here is constant. This initial velocity has to be, give or take, about 21 meters per second or so. So I would have to be zipping off at 21 meters per second, some 70 kilometers per hour or so, for me to hit a distance 75 meters away because I only had 3.2 seconds of flight time. I basically use t here, and you'll notice t has actually jumped between the columns. T is a scalar, so the same time you had going in the vertical is the same time you have going in the horizontal. For the last part of this question here is interested in the final velocity. Like I mentioned, it's tempting, especially when you stare at this parabola here. It's tempting to look like, oh, eventually this parabola is going to be straight vertical, right? Well, no, if there's no x acceleration, if there's nothing that's going to speed me up or slow me down in the left-right direction, I will always be a diagonal at the bottom, and they are always interested in what is the hypotenuse left over behind this triangle here. In the x we just calculated, well, at first, initially it was 21, a little bit later it's 21, a little bit later it's 21. Even by the end of it, I'm going 21 forwards. What I need to calculate is I need to figure out what is the y velocity right before hitting. So now we can use those other formulas. I have the two sides of the triangle, and I can do Pythagoras to find that purple arrow there. So let's use our other equation. We're back in the y, so we're straight in the y column here. V is equal to v naught plus at. You can even use v squared is equal to v naught squared plus 2ad. I just find this formula a little bit easier. So if initially gravity hasn't had time yet, initially you were actually going up or down 0 at the beginning. If gravity starts pulling you down negative 9.8, and it takes you those same 3.2 seconds that we found from earlier, 9.8 multiplied by 3.2, give or take a little bit of rounding here, I'm getting roughly 31 meters per second negative. Right? So it's saying, well, initially you weren't going up or down, but because gravity pulls you downwards for 3.2 seconds, you will then be going 31 meters per second downwards. That's what this negative says. When we actually look at the triangle, you'll notice I kept that as a positive number. That's fine, because my arrow actually shows me my direction. So now I just want you to do Pythagoras here. If we know going forwards is 21 and going downwards is actually 31, can you find for me the velocity, that diagonal direction upon hitting, and calculating that theta there? This is why we did so much work with sort of triangles and trigonometry here. We see that really much in this chapter here. So the velocity here is going to be the root of 21 squared added to the root of 31 squared, right? You do the binomial on the bottom, the addition on the bottom before you take the square root. So root of bracket 21 squared plus 31 squared. This gives me here 37, right? So you notice your final speed is actually bigger, right? It's just 31, but because I actually had some horizontal velocity, the diagonal is actually a total of 37, but we still need to get the angle. I don't want to worry about, oh, should I put positive or negative here? I'm just going to draw the triangle, and then I can just actually give you the degrees. Here's my heading upon hitting the ground. The heading is going to be the inverse tan, opposite over adjacent, 31 over 21. Make sure you're in degree mode again. Divide inverse tan of 31 divided by 21 gives me here some 56 degrees. Do not say south of east. This is a side view problem. So this one here is actually below the horizontal. If you track the horizontal, it's just straight left and right. I'm aiming 56 degrees from the horizontal. You could do a complementary angle. You could have done, 31 first and then 21. You could have found me this angle, and you would describe that angle. 90 minus 56 is give or take about 34 degrees, and you can say 34 degrees in front of vertical. So from the straight up and down, still not north-south, it's just straight up and down. We're going to go in front. It's forwards from the vertical. Usually we do say with the horizontal, but both are complementary. Right? So I'm just going to show you a quick simulation of this projectile motion, and we're going to use this to actually introduce our next setup, which is a football question. Okay, so this is a nice simulation that helps us analyze projectile motion. So far, we've just been studying a meatball style question where we are up on a cliff of some sort. I've been saying it's a car that's driving off a cliff here. In this case here, I've set up a cannon. The cannon itself will definitely accelerate the cannonball here, but once the cannonball actually leaves the cannon, it's like a car that's driving off a cliff here. The cannonball is no longer in contact with the cannon anymore, so there's no more horizontal acceleration. We're just going to follow through that parabola-like shape. So sometimes you can change on your simulation. Here's your starting speed here. We can make it less, we can make it more. Remember, the starting speed here is just perfectly horizontal. I can play around with the height of the cliff as well, so you can play around with that one. We have our distance from the base of the cliff. That's called the range. So right now they have a target there. I can press fire just to get it to go here. I'm going to fire that there just for simplicity's sake here. In this case here, you'll notice based on my starting speed of 15, if my default height was actually 10, I actually have enough horizontal velocity to actually get farther than 15. You can play around with where this is to actually figure out, well, how far that range is. So you can match it up to some of the numbers that we tried to do in the questions, see if we get the same thing. You'll notice that there are little dots here along the pathway here. Each dot here, I think it's to indicate to you 1 second of time. So if you count up all those dots there, it actually tell you the total time of flight. There's some measuring tools we can do here. If I'm interested in sort of tracking sort of individual points here, again, you'll notice that every dot here, in this case here is actually 0.1 seconds. It's actually telling you the range. It's telling you sort of the horizontal velocity, how far from the base of the cliff, and also the height. It's giving you a lot of information sampled at every interval there. If you want to just pull out a measuring tape here, let's say, again, the target does measure directly from the base of the cliff, but maybe I want to measure from, I'm actually just standing over here, and I want to know from me to the person there. I can pull it horizontally there. I can measure this way just like you would a regular measuring tape there. So what I want to show you in this case here is we've been studying, I just pressed reset. We've been studying here, in a perfect world, there's no air resistance. So what's nice about this one here is it actually lets you toggle the different objects, and we're going to find if there is no air resistance, it doesn't matter the object. Let's fire a pumpkin here. So just firing that there. There's my pumpkin splat. Let's see what else they give you here. I can fire a cannonball, a golf ball. It doesn't actually matter the size of it. Let's fire a piano, right? Way heavier and whatnot. If there is no air resistance, you're going to find that it follows exactly the same trajectory. Because with no air resistance here, there is actually no speeding up or slowing down in the horizontal direction. What if I turn on air resistance? When I click on air resistance, like in the real world here, this actually provides what's called a drag coefficient. A drag coefficient acts like a friction force, so that as we actually fly our way through the air, it's the air particles that actually slow you down. So that even though I was saying the second that you leave the cliff, the wheels are no longer in contact with the cliff here, you can't speed up or slow down anymore. In fact, as you cut through the air itself, it's the air particles themselves that actually slow you down. If I just redid that one here, if I did it here with, we had started with a pumpkin, with the air resistance is a little bit lower. The lower the value, the less friction there is. This one here, I'm just going to fire that. Right, so pretty much it follows a similar trajectory here, but given there is the air resistance, whatever starting speed I actually leave the cannon with here, it's encountering a lot of friction. It doesn't quite get as far as normal. If I take now a piano here has a lot more cross-sectional area here. It cuts through the wind. It's not as aerodynamic. As we then fire that one there, we're going to find it too follows a slightly different path. Maybe different, hard to see. Definitely different from the no air resistance case, but even between these two here, there's a difference in air resistance. So you can play around with that a little bit here. Using that simulation here, I'm going to start introducing to you our second setup, which is called a football style question. For a football style question, instead of being on a cliff, what I'm going to do here is I'm going to pull myself down to ground level. I'm going to imagine doing like I have the football here on the ground. I'm just going to launch this football. Maybe there's a set of goalposts here, and I want to just see how high do I want to kick this football here. I can play around with the angle, so I can play around with sort of how far I launch it at. I can play around with my starting speed. What we're going to see, the sort of problematic part in this football question is your starting speed this time will be given as a diagonal. I need to break that diagonal into x and y. Then I can do my component work. I can do my formulas and just the x column, just the y column. Anytime they need you to piece it back together, I can use Pythagoras. So let's see if this one here will give you a nice football picture here. So there we go. We launched at 15. This was launched at a 50-degree angle. To put in this 15 here, I need to break up how much is a horizontal, how much is a vertical. We're going to analyze this question here. Let's just go up to this max height question. So let's go up to, well, it's going to climb. It's going to reach this total peak, right? That's sort of how high I can get. If this were like a football, there's a goalpost there. I need to kick at least higher than the goalpost to actually get it up. We're going to deal with some problems here with the sort of max height style question. And the other style question is, let's forget about max height. Let's go all the way to the end. When we go all the way to the end, this one here will actually be sort of back on ground level again. And we'll see how that works out with the math. So our second projectile motion setup is a football question. Okay, so let's continue on with our notes here. We're going to analyze through our second style of projectile motion. We're going to call this style here a football question. Right? So as you saw in that simulation here, we have just ground level. We have a football that's just sitting on the ground here. You're the player. You're going to apply some force. You're going to actually kick this football up in the air. And just like we saw, it's going to eventually fall through a sort of parabola-like shape. Usually in these questions here, I'm going to give you, here's the velocity that I know, right? So I kick it at 30 meters per second, whatever. The problem, again, is that velocity you'll notice here is in a diagonal. As we start trying to separate, well, because it's a two-dimensional problem, let's make a list of what I know about x, what I know about y. The question is, where do I put in that velocity? In fact, that velocity here is a diagonal. We're going to need to first break down. Anytime diagonals, they're really annoying here. They're going to give you some angle. I'll put numbers to this in a second here. But you're going to actually use the sine and cosine to figure out how much is x, how much is y, so I can actually at least have the starting numbers in the two columns. So let me just put some numbers to this here. Let's say my initial velocity here was 25 meters per second. That's how fast I kick it at. And the angle that I launch it at here, let's launch this one here. Let's make theta equal to 50 degrees. Okay, could have been anything. I just sort of launched at this angle. Again, the trouble is I cannot put that 25 either in the x or the y. That's what I need. So what I'm going to do here is I'm going to take this 25. This vector actually only applies, let's think for a second here. The football here would have just been sitting here had I not kicked it. When I kick it, because my foot is in contact with the ball, I definitely apply some acceleration. I definitely speed it up. However, this speed that they give me is actually, my foot is now no longer touching the ball here. The ball is already being launched at 25. Because my foot is no longer touching it, I cannot speed it up or down from this 25, 50-degree angle. It's as if I cannot influence the ball anymore. So I know the hypotenuse is 25. I know the theta is 50 degrees. Would you be able to find for me how much is x and how much is y? Right. So again, back to our right triangle work here. Well, in terms of the x direction, although the 25 was problematic, it was at a diagonal, I can say the initial x velocity, well, that's just the adjacent side of this angle. Adjacent is cosine, so 25 cosine of 50. While on the other side here, the initial is equal to 25 sine of 50. So you see it was already a little bit more work here because unfortunately the 25 here is up at an angle. So we need to break out the components. It actually means we're actually going forward 16 meters per second, 25 sine of 50 here. Make sure you're in degree mode here. Give or take a little bit of rounding, 19.2, so I'm going to say 19 meters per second. Right? So what I've done here is I knew they told me the football was actually launched at 25. Because I want to study this one here in x and y separately, I can now ignore the 25, ignore the 50 degrees. I can now say, what if I launched you just forwards at 16 and just upwards at 19? That would accomplish the same motion at 25. What I also want to show you here is, although this arrow here looks like it applies for a little while, looks like it follows a parabola. In fact, if you look really closely, the parabola already drops off from this velocity here. This velocity was the initial speed when I kicked it. As gravity has some acceleration, gravity is going to steadily be dropping this number here. My direction here will be constantly changing as I actually follow the parabola. This velocity vector is only true at t equals 0, at the instant that it actually leaves my foot. So for this style question here, again, depending on the question, they're going to ask you two different things. Let's first deal with part A of the question. Part A of the question here is we're going to deal with max height. So I know this football here is eventually going to reach some top value here. I want to know sort of, well, how far from the ground does it reach? I want to know sort of how far away it is. I want to know things about this max height, the time it takes to reach max height. In part B of the question, we're going to totally just sort of skip over this max height. In part B of the question here, we're going to do the total hang time, the total flight time when this thing here eventually actually hits the ground again. But so far here for a max height question, I want to just sort of emphasize that. For a max height question, let's list the variables that we know. What's the acceleration in the x direction? Again, I know I had to kick this football. I needed to get it up to 25. But by the time it's 25, I'm not influencing anymore. This ball here is just flying through the air. Just for simplicity, we're going to say, again, no air resistance. Acceleration is 0, just like your meatball style question. What's the acceleration in the y direction? Well, the acceleration is going to be a negative 9.8. That negative is important because we've been using positive to mean up. So therefore, negative actually means down. So it just makes sure that when you punch in your kinematic formulas, it makes those things go against each other. For max height, if you think back to even our free fall questions from a couple classes ago here, we actually know one more value. What is the speed at this point here when it reaches the max height? Again, this is a two-dimensional problem. In the x direction, it was going 16. So it was going 16 forwards, a little bit later, still going 16. A little bit later, still going 16. A little bit later, still going 16. That's because there's no x acceleration. So even at max height, your horizontal velocity is going 16. That's fine. But what about your vertical velocity? Your vertical velocity here, initially, you launched upwards at 19. So here it is at 19. It's trying to climb at 19. Because gravity is constantly lowering that velocity, you're going to gradually slow down, maybe 15, maybe 10, maybe 5. What is the y velocity when you hit the peak? Just like when you throw a tennis ball upwards, right? It's going to hit the peak. When it actually comes to a stop, in terms of the y velocity here, we can actually say the v final is actually 0. And this is only true at a max height. At max height, the ball is not moving up or down. Now, definitely, it's still going horizontally. It's still going to the side 16. In fact, if you sort of look at the picture here, this part here sort of looks like a meatball style question, right? If I had a horizontal velocity, I wasn't going up or down, and I followed this parabola downwards, you could think of a football question as sort of, it's just a sort of goes up to max height, and then a meatball question from there. I'm going to still show it to you as a football question just to give you some more techniques, some more ways of actually solving the problem, and we'll go from there. So that's the information we know. It looks like I know more information on the y side again. So let's just try it out here. Let's say I was interested in calculating, well, how high do we get? What's the range, the time, right? Sort of the same variables that we were interested in. Because I do know the final velocity, let's actually use equations that have final velocity. So let's go v is equal to v naught plus at. At max height, I'm actually going 0 meter per second. Initially, I'm not going to punch in the 25 because the 25 was a diagonal. I'm only going to punch in the vertical part of it. So initially, it's going to be 19. Gravity is an acceleration negative 9.8. How long does it take gravity to completely get rid of your 19? So I'm going to bring that over there. Negative 19 is equal to negative 9.8 t. We can find the time this way. The time to reach max height, how long until you hit that peak there, is actually give or take 1.9 seconds or so. We can similarly use the other formula here. We haven't used this formula for a little while, but it still works. So v squared is equal to v naught squared plus 2ad. Again, you can say at max height, I'm not going up or down, 0. The y part of the velocity was 19. I need to square it twice. Acceleration of negative 9.8 here. This would end up giving you your displacement. So we have 0. We can use the equation because there's only one unknown there. 19 squared is equal to 361. Negative 19.6, so the 2 times 9.8d. I'm going to move the 19.6 over. 19.6d is equal to 361, and therefore the d is a positive 361 divided by 19.6. This gives you here 18.4. All right. So again, let me just draw you a picture of what we've done. We've been studying this mainly in the y direction. So far, we had our football starting off here. It's going to eventually make it to the max height. I've been studying in the vertical. I've been studying it. Imagine the ball was already just sitting here. I launch it upwards at 19 meters per second. I know because gravity is constantly pulling it downwards. It doesn't care I'm actually throwing it upwards. Acceleration is actually negative 9.8. It's going to gradually take away the speed here. I'm going to start going 15. I'm going to start going slower and slower. By the time I reach max height here, I'm not going up or down. I've just found it takes 1.9 seconds for gravity to get rid of your 19 meters per second. So that means my clock should say 1.9 seconds at this point. The distance in the y direction is it climbs 18.4 meters before it actually comes to a stop. This one here is positive because the height that it actually climbs to is this 18.4 meters. Now that I actually know the time, remember time is a scalar, so I can actually skip over the column here. What if I want to know the x? Well, in terms of the x, again, I don't want to use the 25. The 25 was problematic because it's diagonal, but the x, we had actually broken it down. The x was actually 16. In terms of the x, it's sort of like saying, well, I started off at 16, a little bit later I'm 16, a little bit later I'm 16. I'm just going at 16. Just tell me how long I travel for. D is equal to Vt. If I'm going at 16 meters per second, and you tell me to stop at 1.9 seconds, 16 times it by 1.9, again, give or take a little bit of rounding, gives me roughly here 30 meters or so. That's pretty much all I can sort of analyze with you here for a max height question. So I actually know sort of this half of the parabola. In fact, using a symmetry argument, because the parabola is nice and even, this parabola here is actually just going to fall. It's actually going to make a perfect copy, a perfect mirror image of the one earlier. I'm going to show you a setup here, just sort of asking you for a few other variables here. I'm going to show it to you without symmetry just to prove it to you. From here on out, you can just use symmetry. I can just say, well, if it was 30 meters to get to max height, I'm going to calculate, well, it's going to be 30 meters to get to the far side here. If it took you 1.9 seconds upwards, I would expect it takes 3.8 seconds downwards here. I'm going to prove to you the symmetry so you can use it later on. So this leads us into the next part of the problem here. Let's say part B of the question. This time, what I'm interested in is something called the hang time. The hang time is the total flight time in the air. So you notice I'm sort of redefining my initial and final. For the max height question, I set initial is when I launched it. My final was just max height. Who cares this football here actually falls afterward? In this case here, for total flight time, I do care. I'm going to put the blindfold on here initially at the start because I know most information. I'm going to totally skip over this max height issue. Although I could think of this as a meatball style question and do it like we did earlier, I want to actually leave the initial here because I'm more confident in this 25 here. And I'm actually going to reset my final. I'm only going to take off my blindfold at the really end, when the football actually lands again. So in this case here, again, it's a two-dimensional problem. Let's see if we can list for us some of the variables here. So we have our x column, what I know about x, what I know about y. Because initial is still the same, the v initial is still going to be 16, and the other one I believe it was 19, right? So those numbers didn't change. The accelerations don't change. The acceleration is 0, no x acceleration, no air resistance. The acceleration on the y side is still negative 9.8, that didn't change. Earlier for a max height question, we were able to say that the vf is equal to 0. But that's only because we were actually here, we don't actually climb up or down from that point. This time, because I'm interested in going all the way up, I hit 0. I'm actually going to be speeding on the way down here. I actually will ask you for final velocity later on here, but I definitely won't have a final velocity that's 0. Remember, we're looking at the speed right before hitting. The v final is now no longer 0. This one here is the speed before hitting. We'll come back and calculate that. Looks like I don't have enough variables here, but now if you look at your sort of blindfold on, blindfold off, there is one other thing that I know this time. Let's try to find the displacement. Again, I'm not using the symmetry argument just yet. I'm not saying 30 meters forwards, oh, it's going to be 60 meters total. I'm going to pretend I don't know that just yet. What about the displacement in the y direction? From me putting on the blindfold, the football is on the ground. When I take off the blindfold, I know this football here went up and went downwards. I wasn't watching it. When I take off the blindfold, you'll notice it's back on the ground. We are exactly at the same ground level as where it was launched from. So therefore this time, although I don't know my v final anymore, I actually do know for this total hang time problem here, the total distance is actually 0. And that's actually going to save us a little bit here in terms of the math. So that's the information we need to know. Because we know d again, we're back to using our initial equation. So let's go. D is equal to v naught t plus 1/2 at squared. The math is slightly more challenging, but let me walk you through this. Because the football is back on ground level, it's no higher or lower than where it began. It's going to be 0. realistically, it did climb, it did come backwards, but your overall displacement, hey, you're back on the ground, so it's going to be 0. Your initial velocity, again, I don't use the 25. The 25 was a diagonal. I just used the y part of the diagonal, so 19. Again, using symmetry, I could have already been 1.9 second upwards, so it's going to be 3.8 seconds downwards. I'm going to pretend I don't know that yet, so let's just go t plus 1/2. The acceleration is negative 9.8 t squared. Let's clean this up a little bit here. 0 is equal to 19t minus 4.9 t squared. Right? So it's doable, right? It's one equation, one known. I should be able to solve for t. Only trouble here is this time, unlike a meatball question, your initial velocity was not 0. 0 didn't kill off this t term, so you couldn't just do a square root. I can't kick the t term over to the other side because I want to collect up all the t terms. You might think about dividing by t, but in general in math, when you divide by a variable, you tend to lose solutions, you tend to lose answers. So in this case, what I'm actually going to do, because I see there's actually a t term in both these variables, what I'm going to do is I'm going to factor that t term out of the binomial. And what's going to happen there is I'm going to have 0 is equal to t. What's left in the bracket here is 19 minus 4.9t. So you could have even done this factoring here earlier as well. But the nice thing about a football question here is now I have t multiplied by this thing. I have two numbers being multiplied. The hint here is it has to give you 0. Can you give me an example of two things that multiply to give you 0? Well, it would be like 5 times 0 or 10 times 0. You actually realize one of the numbers have to be 0. So because two numbers have to multiply to get 0, either this first term is 0, so either the t is 0 itself, or this other binomial, this 19 minus 4.9t, this bracket here has to equal 0. That's the only way for two things multiplied to actually hit 0. We're going to solve through the math here. 19 is equal to 4.9t. The total hang time is now going to be 19 divided by 4.9, which is that 3.9 seconds, 3.8 seconds, like we had predicted from earlier. Why do I get 2 times out of this? Again, this is just math, so mathematically there are 2 times that the football is on the ground. Well, actually, at the beginning, when you launch the football here, the football is on ground level. We're calling this displacement here d equals 0, so height of 0. Well, of course, at the start, it was 0. That's not the point I'm looking for, though. I want to go all the way up and all the way down. When is the football here back on d equals 0? Well, it takes some 3.9 seconds away. And again, give or take a little bit of rounding, we had said it was 1.8 seconds up. Was it 1.8? 1.9 seconds up to the top here. You'll notice that 1.9 seconds, if I double that one, that gives you 3.8, 3.9 seconds or so. So that sort of proves to you the symmetry. We didn't need the symmetry here to actually solve it, but now we know the total hang time is actually 3.9 seconds. I can ask you further questions. Well, what's the total range? How far should my friend be standing so he can catch this football? Well, in the x direction then, d is equal to vt. The velocity has always been 16. This time you're going to give me twice the time, right? 3.9 seconds. So if I go 16, I multiply by this answer. I'm going to need to be 62 meters or so. And again, looking at the symmetry of the problem, I had done a little bit of rounding. It was 30 meters forwards. You see that's roughly 60 meters to go to the far side. So again, the symmetry does end up working, but I'm showing you this way of factoring so that we actually don't need to use symmetry. We have that range there. That's pretty much all the question. We have one last problem here. Let's calculate the V final. Now, based on symmetry here, I would imagine whatever my diagonal upwards is probably going to be my diagonal downwards, right? But let's just solve our way through. Because the final velocity, let's say this is part C of the question, I want you to calculate the final velocity. And again, I want to emphasize before hitting, not after it collides and rebounds and slows down and 0. Okay, the final velocity is the fastest speed it's going. Well, in the x direction, it's boring. In the x direction, it's 16. A little bit later, it's 16. A little bit later, it's 16. It's just 16 sort of all the way along. So even at this point here, it's still 16. Let's find what's the v final for gravity, right, in the y direction. And let's use our Pythagoras and put that triangle back together. So back in my y column, right, we can just sort of keep separating the columns for you here. So back in the y direction here, v is equal to v naught plus at. Earlier we used this formula for max height. We knew the final velocity was 0. This time I actually want to know the final velocity, not just at the max height. I want to know if you give me 3.9 seconds of flight time, what's my final velocity? Initially I was going 19. Gravity is an acceleration negative 9.8. The time is going to be 3.9. Let's find out what the vertical velocity is. 19 minus 9.8 times 3.9. Give or take a little bit here. This is negative 19. Well, that makes sense because this is actually going downwards. And what would you get if I combine a triangle? We're going 16 forwards, and we're actually going 19 downwards. If you do your Pythagoras again here, I can leave that for you to try here. This is exactly a mirror image of what we had earlier. You should find that the C is the 25 meter per second that I had launched it earlier. That was 50 degrees above the horizontal. You should find that this theta is also 50 degrees below the horizontal. Right? So slightly different math here. We can deal with a max height question. We'd have to do a little bit of factoring because this t term here didn't die out. But same sort of analysis here. Whatever I know about y, I can do the equations, keep the x's by themselves. Anytime I need to put them together, I can use Pythagoras to find the final velocity. All right? So I'm going to leave it off there. If you have any questions, let me know. Thanks, guys.